My name is Andrea Manconi. I'm very happy to deliver this lecture today in this joint international line training program. I hope that my slides are visible and my audio is fine, and I can proceed with a short introduction about myself. I'm working in the Research Institute for Snow and Avalanche Research at WSL SLF, located in Davos in Switzerland. And as you can see here in this slide, I'm part of the CERC Research Institute, which is working mostly on climate change, extremes, and natural hazards in alpine regions. We have several research topics and core research areas, and you can see here summarized. And also you can have a better view if you will go to the links. Just about my research activity, I wanted to give an overview of what is my main expertise. I work mostly on landslide deformation monitoring, as you can see from this slide. And I've been working also in the past on other applications, especially related to earthquakes and volcanoes. But currently, in the last 15 years, my focus was on landslides. And that's the reason of the lecture today. And specifically, I will focus on the use of radar interferometry for landslide deformation monitoring. Just a quick outline of the lecture. I will give a brief introduction about the topic and then focus on slope deformation, expecting that you have already heard about the basics of radar interferometry. I will not repeat too much about that, so I will stay into case studies. I want to show you several applied examples where we use radar interferometries and different methodologies that can be applied for detection, monitoring, and also when we have acceleration of slope deformation that might be close to a failure context. Then I will give an outlook and deliver some conclusions. I think this video has been already shown by many people, and you see what a landslide failure might look like. So that's really recent and happened in the Swiss Alps, and specifically in the mountain called the Klein Nesthorn, and it was destroying completely a village, Avnemonde. These kind of failures are quite rare, fortunately, but they are happening more and more in alpine ranges, and that's the reason why it's important to detect the initiation of surface deformation and to evaluate the potential of such slopes to failure and cause consistent damage and also victims. How do we deal with these landslide scenarios? So usually we think of the model of landslides that are evolving over time, depending on the predisposing conditions, so depending on the geology and the geomorphological settings. But then we have some external factors that might accelerate or slow down the evolution of the landslides and maybe lead suddenly to an acceleration that would lead to a failure. So there might be several external factors like heavy rainfall, or there might be earthquakes also triggering, or this can be because of snow melt, excessive snow melt, or because of deglaciation and permafrost. And on the right, you can see my graph here. This is the model that we have in mind after the initiation of a strain, so of a deformation in the mountain slope. We have an initial destabilization, which is the primary creep phase, then a steady state status, which is called the secondary stage, where the velocities are steady state, and we don't see a lot of changes, still permanently active, but not really having clear signs of acceleration. And suddenly, depending on specific conditions, we might experience an acceleration and going towards this exponential phase that might lead to failure. It's not always that the first time that we have this initiation of the exponential acceleration, we might reach failure, but it's a progressive process that is happening in the mountain range. And this is what we would like to monitor with different techniques. Specifically in Switzerland, we have the guidelines that are from the Swiss Federal Office of Environment for slide processes, and this can apply to mountain slide processes and also to lower range processes. But in general, you see that the intensity, when we talk about the hazard, so which is a combination between intensity and probability, so the intensity of slide processes is clearly defined based on velocity. And that's also the reason why we are really interested in methodologies and techniques that might indicate the velocity of slopes. And for sure, radar interferometry is one of the key techniques that can help us. Just briefly to recap, so we know that by using radar interferometry, we can detect changes in the order fractions of the radar wavelength, which means that we can get subcentimetric displacements along the satellite line of sight, or if we have a combination of different satellites, we can also have specific directions of the surface deformation. And theoretically, we can go to subcentimetric level in the so-called coherent areas. Why differential interferometry is important in geohazards and for this reason also in landslide applications. We know that long-term and short-term deformation are characterized in geohazards, and as I said in the model of creep for landslides, this is really a clear indication of a potential destabilization. As I said, the InSAR is able to give us subcentimetric measurements with large spatial coverage and also applicable to remote regions. And in addition to that, it's a technique that can work day and night and with all weather conditions, so it's suitable also for some assessment in emergency scenarios. We have several satellites that can be used for these applications, and I guess in your course you already touched a lot of them. You see that we can do a historical analysis, especially with satellites which are with C-band, so with 5.8 centimeters wavelength, like the IIRS mission or the RADARSAT mission and the ENVISAT mission. But for sure, the Sentinel mission has changed our perspective in every field because we can go not only into this historical analysis, but we can work also in the direction more of monitoring. That's the reason why we change a little bit the perspective also in the landslide community to be capable of using such technology, not only for back analysis and understanding processes, but also to monitor the evolution over time. You see also additional satellites that I'm mentioning here, so very high resolution satellites and constellations that are nowadays more and more available, commercial satellites and that can be tasked for specific scenarios. And I will show you an example also of the use of these satellites for a large landslide here in Switzerland. And we know that differential interferometry alone can be used for mapping and identifying some slope deformation, but for sure the persistent scatter interferometry has changed completely also our view on how to monitor over time the evolution of surface deformation. And I'm showing here the example of the European ground motion, which is available and free, and you can use the information that is there. And this already showing both the good and the cons that you have with persistent scatter interferometry, especially in high alpine areas, where some of the areas are visible and can be monitored, and all the areas, for example, when you have vegetation or when you have very rapid deformation, cannot be monitored consistently. If I go back to this example, you see that Switzerland is not covered by the EGMS. And this is because Switzerland is not participating to the Copernicus program. At the moment, there is a specific program that is being developed by the Swiss Federal Office of Environment, and the data will be delivered soon. So we will also have a similar platform where we can monitor the information about surface deformation in the Swiss Alps. But what are the scenarios that we have when we use spaceborne differential radar interferometry? So the first scenario would be a kind of on-demand processing based on a specific event. So an anomaly can be detected because of specific observations in the field, or maybe looking at all the data sets, and we can process targeting over this area. And another possibility would be that there is a disaster or some failure, and we get the information afterwards by using the differential interferometry. Another possible scenario is that we want to do a regional or a more local analysis, just having the information about surface deformation over a region. And this is so-called a survey approach. And we want to process all available images over a target area, and the results can be analyzed to detect and map the anomalies in the surface deformation, and we can then associate this information with additional data sets that can be geological or geomorphological data, or additional data sets that can be explaining the spatial and the temporal deformation pattern. Another approach would be that we have an automatic processing strategy every time there is a new radar image that is available. And this is more going into the monitoring approach. As I said, with Sentinel, this started to be really more and more applicable. And in a specific case, we can also have thresholds that can be defined and can be used to identify anomalies and basically to have a set of actions that can be taken in case the thresholds are overcome. Now, I would like to show you some examples, some ideas, and some specific work we have been doing on these kind of scenarios. And the first example I would like to show is the mapping and investigation of landslide in the high Himalaya of Bhutan. So that's a project that has been part of a PhD project several years ago at ETH, and co-supervised by myself. So you would ask why we wanted to work in Bhutan. So it's quite clear that in Bhutan, like in all the Himalayan range, we have a specific problem with landslides and that are touching transportation corridors. You can see some pictures here of large rockfall activity that might be associated also to deep-seated gravitational slope deformation that is damaging roads and infrastructures that are quite new. And here you see another example when you have the monsoon activity. Of course, a lot of material is eroded and can fail. And you see the typical example in the Himalayan range when you have a landslide and you need to wait for passing in a road. This is a range of possibilities, but of course there are additional reasons. And in Bhutan, there are several projects, but in all Himalayas, and this is part also of the climate change scenario where we have a lot of glaciers that are melting and the water can be used as a resource. And you see the power plant plans that have been done here for Bhutan. And when you have such a big engineering projects, the perturbation that you have on a specific point is causing also changes upstream that might cause additional landslides. We know quite well this in the Alps because we have been in this situation in the 60s. We had a lot of projects and several landslides were reactivated and also big damages were occurring at that time. How can we use radar interferometry in such a scenario? So there was a work from Benedetta Dini that I also link here, and you will find the references at the end of the presentation. Well, we have approached this area of the high Himalayas of Bhutan by processing all possible data sets that were acquired of the data. This ranges from IIRS to Envisat data to also ALOS pulsar. By processing with standard interferometry, we could detect patterns of deformation, as you can see here in this slide, and then associate this to a digital elevation model, in this case, an accurate digital elevation model that can be used to trace specific predisposing factors. And here you see also some cross sections trying to analyze the state of activity of the slopes. And by doing this on a large scale, on a regional scale, we wanted to have finally a map that is so-called likelihood of activity. So this is basically the final map where we have several landslides or several parts of landslides that were active in a specific period of time. And this color scale is just showing how many times we found interferograms that were showing deformation in this area. And by having this proxy on activity, you can just have some indication of what might be the causes, might be related to structural activities or some faulting, or maybe to declassification that is triggering also some slope deformation in the area. Another work we have been doing now, this is in India, in the Uttarakhand state, is also with similar purposes. We wanted to identify the hazard scenarios in the Uttarakhand related to rock and ice avalanches. And also in this case is in a region, the Bhagirathi Valley, where a lot of damming has been hypothesized and a lot of plants are already operative. So, and that's the reason why we wanted to have an idea of the surface deformation in this area. And again, it's a very large area. It's not easy to do monitoring with other technologies, and that's the reason why radar interferometry from satellite is really important. As you can see here, we processed Sentinel-1 data. We worked on the period between 2018 and 21, and we had several interferograms. So really, again, the basic standard interferometry just to check the surface deformation pattern, and process ascending and descending orbits, having several interferograms with a temporal baseline less than 1 year. So the aim was to identify landslides that are permanently displacing and that are causing potential damages to infrastructures, or if they would accelerate, they would also cause some damage. Here I can show you an example of how we treated this data. So you see this example close to the village of Naga in the Bhagirathi Valley, and with some interferograms that are showing patterns of surface deformation for different time periods. And depending on the time period, we can also start to see some deformation that is not only affecting the lower portion of the landslide, but also affecting the entire deep-seated gravitational slope deformation that can be mapped here. And if you take all the velocities that are extracted, in this case, visually and just with a qualitative approach from these interferograms, you can build up graphs like this, where you have some velocities more or less stable over all the time period, but sometimes you have some accelerations that can pop up. And this is an indication of a potential reaction and triggering due to rainfall activity or snowmelt. And this is what's being investigated now, just to understand whether there are some impacts of external forces that might accelerate this. It's not a time series like you would have when you apply persistent scatter interferometry, but it's still giving you an indication of what is the evolution over time, and is giving you also an indication of the spatial extent of the landslide. And this is the important point that I would like to do today, is that sometimes we forget that the interferograms are one of the most important source of information, because we process the interferograms and we finally generate the persistent scatter interferometry map, which is very accurate to the millimeter level, but is missing, especially in mountain areas, the spatial patterns that might be very useful for the interpretation. Another area in the Uttarakhand, that's now in the Patal-Ganga Valley. As you can see here, there is another area where we focused because of another reason. So there was a large landslide blocking the road near the Patal-Ganga and Landslide tunnel. And we were processing this data set and found out that actually there is a very large deformation pattern that is affecting in this focus area. And again, also here, if we just look at the landslide from the optical point of view in this Sentinel-2 image, you see that you have vegetation. Also, the orientation is not favorable for landslides, because the pattern and the expected deformation would be mostly in a north-south direction. But still, we can get information if we process the interferograms. And if we look at specific interferograms, we can have a very accurate identification and evolution of the surface displacement. If we get such information in the north-south direction, it means that since we know that in the vector, in the line of sight, we have a small amount that will go into the line of sight of the satellite, we can already infer that the deformation might be much larger than what we can measure with the Sentinel data here. And here we can see it both in the ascending and also in the descending. And in the descending, we see that the deformation pattern is affecting up to the upper portions of the landslide, meaning that there is not only a large landslide that is occurring here down, which will be this feature that you can track here on the left portion of the landslide, but it's more a deep-seated gravitational slope deformation, and this is a subdomain with higher velocity that is affecting the entire slope. Again, here the interferograms are a very good indicator of what is the spatial pattern and giving also some information about the temporal evolution of the displacement. So it's not yet monitoring, but it's giving you a survey scenario as we discussed before. We are currently working on a project that would automatically mapping the deformation of radar interferograms with artificial intelligence. I mean, the work that I've been showing so far has been done manually by experts. And here you can see just an example on a canton in Switzerland where we are testing artificial intelligence and also comparing the performance between the model and experts that will map these patterns in interferograms. Maybe you know that it's not easy to identify. It requires a lot of experience to work with radar interferometry, but we are trying to train models so that can learn and map automatically this kind of patterns. And at the moment, the results that we are really encouraging. So we are really hoping that we can get to a solution soon that would simplify the mapping of interference. Now we move to Switzerland, and we move to an area that is really important in Switzerland. So it's the Great Alleged Glacier, where we have clear changes due to the climate scenarios. And you can see the evolution of the glacier is expected to disappear in the next 100 years. We know that in geomorphological models, if we have such a release of the glacier, such a retreat of the glacier, we might have a reaction of the slopes that are close by, and this is causing a lot of surface deformation. Specifically close to the tongue of the Alleged Glacier, we have a landslide, which is called the Moss Flu landslide, that in 2016 has accelerated consistently. You can see from this video. The deformation was monitored with a total station that was installed there before. It's a rare scenario where you have some instruments and you can really see the evolution of the displacement that is going to be exponential, as I've shown in the creep model. And you see that the rock mass has been completely disintegrated and you have a lot of rockfall activity and large deformation patterns. What can we do here with interferograms and for example, with persistent scatter interferometry? Well, if you would process the synthetic aperture radar data acquired from Sentinel in the period of this evolution, you will get something very similar to this map, having few points that are showing some deformation in the area of the landslide, and mostly a linear evolution of the displacement, although we know that the exponential evolution was clear from in situ measurement. Why this is happening? When we have very large surface deformation, we know that the so-called phase aliasing effect is occurring. We cannot really follow the evolution towards the phase cycles, and this is causing a decorrelation of several points, and that's the reason why we don't have a lot of points in the area. But also a systematic underestimation of the surface displacement. We try to make a summary of this effect in this paper in 21, where we have this graph that is showing at the evolution of, so the exponential evolution of the displacement. So for example, in a very rapid scenario with 2 years and some oscillation due to seasonal changes, and a longer evolution, so a long-term evolution up to 20 years towards the exponential evolution and failure. that is then also superimposed with some cycles that are the seasonal cycles. And you can see that by using several satellites, we can set some thresholds that would be the phase aliasing limit that we can systematically compute. And you see that after a certain level, we cannot follow anymore the evolution. So we cannot monitor the evolution because of this threshold. That's a very important limitation that we need to think when we're working in alpine landslides, but also in general with every surface deformation process, because it might give us some misleading interpretation of the processes. Still, if we look at the interferograms in this area, instead of looking at the persistent scatter interferometry, we can track the evolution of the displacement. So you see here a clear deformation pattern of some centimeters, and then suddenly disappearing this pattern because of a decorrelation. But still, we can make a comparison between areas that are very coherent and not deforming with areas that are deforming more than a certain level. Just again to say that interferograms are still a valuable tool that can be used in case the persistent scatter interferometry is not providing information. So we can always go back to the source data, which are actually these interferograms, and try to track the evolution over time. Another example that I can show here for telling you a little bit more about surface deformation processes in alpine scenarios is the Brienz-Brienz-Haus landslide that occurred in June 23. There was a big failure of a little bit more than 1 million cubic meters, and it was almost touching this village, Brienz, that is located on top of this slope. And fortunately, this was evacuated, and unfortunately, still evacuated because there is a still large hazard that this area up would fail, still deforming with several centimeters per day. And that's the reason why the village has been completely evacuated, to avoid that it might be not only structural damages, but also damage to the people. In this area, there were major concerns already since years because of the evolution of the displacements that has been monitored with in situ displacement. So what we wanted to understand in such a scenario where we have a very good monitoring infrastructure is what is the potential of radar interferometry when we can really evaluate the quality of the results by having such an infrastructure for monitoring, for evaluating the performance. So, and that's the reason why we have processed first the persistent scatter interferometry. We just process all the images with the Sentinel, and we have a similar scenario like I've shown before, where we have a few points that are remaining because of the intrinsic limitation of C-band. And the points that we have here are also showing this a linear evolution of the displacements, although we know that the evolution of displacement is not linear. This is something that has to be, again, considered, and that's the reason why we wanted to process the interferograms and not going into the persistent scatter interferometry, because we know that if we want to do a systematic monitoring, we have a lot of limitations. So, of course, there is a problem in spatial resolution. Well, of course, we know the problems that are caused by the geometric distortions. Again, we know that there might be the correlation because of vegetation and snow, and the focus is again on this problem, the phase aliasing problem, where we have very rapid deformation that might be not followed by the radar interferometry because of the wavelength of the satellite we're using. We approached this area by using a relatively simple stacking analysis. So using interferograms with similar temporal baselines, we were able to at least identify some patterns of deformation in the upper portions of the landslide where there was the failure afterwards, and also in the lower portion of the landslide. As you can see, depending on the track we are looking, also in this case, we have a south face slope, and the deformation pattern might be different because of the horizontal displacement that are quite large in this case, and the surface deformation pattern needs a little bit of interpretation to understand what is the kinematic evolution of the landslide. Here, what we can see is a clear trend towards 2020 of deformation, and this is something that it's already more than what you would get with the persistent scatter interferometry in terms of spatial distribution of the surface deformation. If we use only differential interferometry and we compare with GNSS data that we have available on the ground, you can see that depending on the track, here we have an ascending track and two descending tracks that are covering the area. Up to a certain level, we have a good agreement between the ground-based data and the satellite interferometry. But you see these red lines that are here are actually the phase aliasing, considering a 6 days or a 12 days baseline. And you see that after these red lines, we have deviation between the radar interferometry and the GNSS. We are going to have meters per year, and of course, after a certain level, we cannot follow anymore. So it's quite clear that we have a limitation that depends on the surface velocity. Again, to try to cope with that, we want to combine the information we have from radar interferometry with additional information that can come from all the data, like, for example, aerial data sets or all the satellite or optical images that can be acquired of the area, and approaching that with the digital image correlation approach that is not affected by the phase aliasing, is just affected by the spatial resolution of the data. So if we have a very good ground sampling distance, we can get information of the displacements. And we had LiDAR data sets that can be used in this scenario. So we combine the LiDAR and the drone data sets. So here the evolution of the displacements is quite clear after the failure. And we can use this data set just to track with the digital image correlation approach, the displacements, and combine by having different orientations to get the three-dimensional pattern of the surface deformation. And this is what we have done here. You can see the combination between the stacking that I've shown before, plus the digital image correlation, which is getting to a three-dimensional pattern that is much more suitable for interpretation, especially when you have deformations that are in the order of meters per year. And in this case, we can have two different periods of about 3 years, and we can see the evolution of the landslide and the clear acceleration of the upper portion that was the one that then failed in 23. Now, if we compare again the results between the ground-based monitoring and the combination, so the 3D components that can be used for, can be extracted by using the stacking plus the digital image correlation, we see that still in the east-west, we have some problems for some points that are still too fast, and this is because the main deformation is actually in the north-south direction. Here we have a better representation of the north-south until we stay in a certain range of velocities. Here you see it's much better than before, but still we are not reaching in a line that would see a perfect agreement between the in situ and the remote sensing approach. And the same also for the vertical deformation. And this is because the digital image correlation cannot compensate the vertical deformation because we are just looking at the plane where the deformation is occurring in the LiDAR data set. So we'll need additional processing also to cope with the vertical displacement. So this is another important message. So even if you combine with different techniques, depending on the kinematic evolution of the landslide, you might have a misleading interpretation due to missing information due to the clear limitations of the data set. I mentioned at the beginning that we have a new era with some radar satellites that have a very high resolution. Here is just an example of the ISRO, Capella Space, and Umbra. And they are useful, especially in the scenario that I mentioned before with the digital image correlation, because we have a very high resolution. So we are going to the 50 centimeters pixel size or better. And of course, by using this information with digital image correlation, we can track deformation that is in this same order of magnitude. Here's an example of the ISI image in the spot high mode. And you can see that it looks like a picture, but it's a radar image. So it's an amplitude image where we have the village. You see clearly the slope, and you can see even the vegetation quite clearly. And it's just because of the resolution, of the very high resolution. How can we use this information, especially when we have a lot of images that are acquired in this time range? So you see here the lines are representing the sentinel data, which would be between 6 and 12 days. And here, all these triangles and points are showing the ISI dataset that has been on demand acquired in the period when we had a clear evolution that might reach a failure, and then it finally reached the failure in the 15th of June 23. We have an average revisit time before the failure of about less than 2 days, and in some cases also in the order of a few minutes. And what you see is that the angle of view is a little bit different. So we need to combine images that they have the similar line of sight if we want to have good accuracy on the displacement. So you're just showing a short animation of what is feasible just by doing the animation on this very high resolution. You see this pattern here that is moving, and then you have the failure. So it's already visible with the eyes, and that's the reason why also the digital image correlation has not hard job to detect this deformation. And here you can see the evolution in the last days before the failure, where you have this pattern that is increasing over time and then suddenly reaching to the point that is fading. And we're talking about now meters per day, not anymore meters per year. So we have a completely different range that we have to cope with. So that's the reason why in this specific scenario, in the accelerated deformation, we cannot use the standard satellite interferometry anymore, because it would be too quick, and we could not follow the deformation. But if we have such new satellites with high resolution in space and time, we can aim at having a monitoring of this last portion before the failure. It's just an example of the comparison between what you can get from a ground-based radar that is installed in the area. You see this is the green line, is the ground-based radar. And here the pixel tracking or pixel offset, just having different combination of the data set that has been acquired. And you see that we have a fair representation of the acceleration until the failure. And by using the standard inverse velocity model, which is a very simplified way to try to infer the slope failure, by using the green line here, which would be the ground-based radar acquiring every 4 minutes, and the satellite data, we have a good agreement, which means that having an increased spatial and temporal resolution will help us also in cases when we have very large deformation before the failure. Summarizing the information I provided you, so the reconstruction of the spatial and temporal evolution of a complex lens scenario using C-band InSAR might be often incomplete, and this I've been showing by listing some examples in the Swiss Alps. And you might have substantial underestimation of specific components, especially in the north-south, which would lead to incorrect evaluation of the surface deformation field. So it needs always to be considered, and the monitoring applications can be strongly affected. One possible way would be combining the standard interferometry with digital image correlation, but some problems can remain, as I've shown in the case of brilliance. So the improved spatial and temporal resolution is really the key to disentangle such complex situation. So the very high spatial and temporal resolution provides more information. So we are in an area where a lot of satellites have been launched, and there will be more and more missions, also considering the new missions in the L-band range, like in the NISR mission or the potential ROS-L from ESA in the future, which might help to cope with some increased velocities. but still we would miss the increase towards the direction of meters per day. So meters per day is something that would be not feasible even for the new satellites if we are not going into the very high resolution like I've shown with the ISI data. With the pixel offset analysis on the very high resolution data, we can also reach that level. Of course, this is a completely different scenario. So it's not open data. It's something that is commercial. So the cost would be very high. And we also attempted some volume estimation of the very material while using InSAR in the ISI, but at the moment we have still some problems in the estimation of the volumes released from the source area, and this is because so they are very steep, and the decorrelation is occurring in such areas and would not allow an accurate representation of the volume field. Here you see the references that I mentioned in the slides, and I'm concluding, so I would be happy to reply to some questions, if any.